Hello guys, how are you doing today? Today we're gonna start talking about chapter 9 in our program of study, and chapter 9 is basically about center of gravity. And who says center of gravity, also we have to talk about center of mass and centroid. That's in chapter 9. Usually I start my classes by saying, oh, have you heard about center of gravity before? And people say, no, I haven't heard about center of gravity before. Okay, so let's talk about a hypothetical situation. Let's say that imagine that you are in the road and then you're taking a curve, a really close curve like that. This is the road, and then you're gonna come here with your car. I'm not very good at drawing cars, so let's say that this is the car, these are the lights coming forward in that car, and you're going in this direction and you're taking that curve. And let's say that you are making 50 miles an hour in that curve. Yeah, I know, don't try it. And let's say that you're making 50 or 60 in that thing, and then you're using a Camaro or a Mustang. What is gonna happen? Well, nothing. You're gonna have the car skidding a little bit maybe, and it's gonna take the curve and nothing happens. And then imagine that car, now you're gonna do the same experiment again, but instead of using a Mustang or a Camaro, you're gonna use a Liberty, a Jeep Liberty or a Jeep Wrangler or one of those Jeeps. And you take that curve at 60 miles an hour, and then everybody starts laughing. Oh no, what happened? It's gonna flip over. Why is gonna flip over? Why are you saying that? And they say because the center of gravity is higher. So you heard about center of gravity before. That's immediately what I say. You heard about center of gravity before. What is center of gravity then? And they don't know how to explain it. And then I go to another topic and I say, okay, imagine now that you know what the center of gravity is because you don't know how to explain it, but you know what it is. Let's say that you have a book, and in that book you have to find the centroid of that book, the center of gravity of that book. Where do you find it? Where is the center of gravity of this book? Oh, at the center, because it's a rectangle. Well, assuming that everything is homogeneous and the density is the same and the distribution is the same, yeah, at the center. You see, I'm putting my finger at the center and I'm keeping that book balanced in that way, exactly like it is. You see that? No problem whatsoever. So at the center, perfect. Now imagine that you have something like these squares like that, triangles. I don't know the name in English. I always forget the name in English for this. But you know those instruments that are like that, and you use for drawing. I have one here. Look, it's not exactly like that, but I wasn't planning on using it, but I found it right now. So let me take it out from the part. Now you have this type of shape. There you go. This type of shape. It's a triangular type of shape with that weird section there. How do you know where the center of gravity of this is? Oh, I know it's gonna be somewhere here, somewhere around here, but it's not gonna be at the center. I know it has to be somewhere over here. And by the way, you know where is that thing? How do you know it? Because we studied before when we talk about distributed loading, and you say, oh, when I convert a triangular distributed load and a concentrated distributed load, the total force is gonna be placed here, and it's gonna be 1/3 of the base or 2/3 of the base, depending on what is the. This is the base, and same thing with the height. Same thing with the height here. 1/3 and 2/3. So you knew that from before because we discussed that, but you know even by empirism, by your knowledge, your previous knowledge in life, you know that basically it's gonna be a point there where you're gonna be able to keep the balance. And if you get other shapes, I don't know, you get this type of shapes, for example, and you wanna say, what is the center of gravity of this thing? I don't know, but I know that I can keep the equilibrium and I can balance it somewhere here, or somewhere here, or somewhere here, and then I can get the center of gravity. Now, how will you get the center of gravity, for example, of this? I say, well, it doesn't matter, I cut the shape and I put it in my finger and I balance, and that's the center of gravity. Yes, that's true, but what I didn't tell you is this is a 2-ton rock, and now you can't put it in your finger. So how do you find the center of gravity of a shape like that, a regular shape? Well, if you want to do the empirical procedure, it's exactly the same. You don't put it in your finger, obviously, but you hang it from some place, maybe from a crane, something like that, and then you let it look for the equilibrium. If you let this look for equilibrium, this is going to be shifting I don't know. Hopefully this is gonna be close shape to whatever I have. Imagine this is the same shape, okay? And when this thing looks for equilibrium, you draw an axis over there with the vertical, like that. And now what do? You hang it from here, and you cut this one. So when you do that, the same shape is gonna come here, and now it's gonna try to look the equilibrium from the other point, and I don't know. Let's say this is the same shape again, because it's not supposed to change the shape. And originally I have an axis that I drew before this axis, and now I draw a new axis in this direction, and wherever those two axes matches, that is the center of gravity. Okay, so what is the definition of center of gravity? Usually in class I have a longer discussion, but I don't have too much time because it's a video and I don't want to make it too long. But usually the center of gravity, or if you want to know what the center of gravity is, you can say that the center of gravity is not the place where the weight is concentrated, because that's what people say all the time, and this is not the definition. Oh, but I thought that you say that when you put the book here, basically what you are doing, you are putting your finger at the center because in that place is the weight concentrated. No, this is not what I said. I said that you look for the point of equilibrium, and that's exactly what you do. If you look for the point of equilibrium, which is in this case wherever the two axes meet, or the three axes, if you do it now in the third direction, is going to happen. And if I do it from any other direction, any other axis is going to intersect that part also. So the center of gravity should be that point in the body, what is keeping the balance. That's it. Just is keeping the balance. What is the balance? The balance of the forces and the balance of the moments. You can say that is the point where if you eliminate every single weight from any single other point and you put it there, that will produce the same effect. Wait a second, we covered that? Yes, we covered that. We covered that in that chapter. That is when we were doing converting a system of forces in a single equivalent force. That's exactly what we are doing here. So how can you, our goal, our objective is coming from with one approach that allows us to calculate the center of gravity. So let's say, what is that? Let's say this is the same rock that I was using before over there. Now it changed shape again. So what we're gonna be doing here is I want to divide this in a bunch of tiny pieces. That's what I'm doing here. And if I do that, I know that every piece, let me use this one here, every little piece is gonna have a particular weight. Weight 2, weight 3, weight 4, weight n, and I know that every single of the pieces is going to have a particular weight. Theoretically, if I don't lose any part of material when I do that division, because I shouldn't, then I can say that W1 plus W2 plus W3 plus Wn, that has to be equal to the total weight. And that's nothing new also, because basically we're saying, no, if I take the total weight here, the division of every one of the parts has to be equal to the total weight. Perfect. Now you can put this in, I don't know, more mathematical terms, elegant terms. The summation from I equals 1 to n of Wi. That's the total weight. Perfect. If you realize what we're doing here, if I pass this to the other side, basically what we're doing is summation of forces equals 0, because I'm putting a force exactly where the weight is, but don't worry. Now for equilibrium is the effect that this is going to happen. Now I can imagine this shape with all these different forces applied at the centroid, or at the center of all of these small squares over there, and I know that the summation of all of them is going to be equal to the total weight somewhere over there. Now if you remember equilibrium is not only about summation of forces equals 0, we have also summation of moments equals 0. Summation of moment has to be equal 0 with respect to what point? With respect to any point. So what I'm gonna do is I'm gonna set a system of axis for reference here, x, y, and that this is going to apply to x, y, and z also, but for simplification purposes, I'm just doing it here. And now I can say that if I have a w here, that w is separated from my axis of reference a distance x1, and this other w2 is going to be separated a distance x2, and x4, and x3, and xn, and the total weight is going to be somewhere over there in that location, and I'm going to call that location either x bar or xcg. Now if I do the same approach that I did with the forces, now I do it with the moments. If the effect of this weight placed there is going to be the same effect of each one of the forces placed in the corresponding places, then I can say that x1 multiplied by w1, remember vertical force, horizontal distance, plus x2 multiplied by w2 plus x3 multiplied by w3 plus xn multiplied by wn has to be equal to x bar or xcg multiplied by the total weight. And this x is going to be the x coordinate of the center of gravity. So if I put this in mathematical terms again, x1, w1, x2, w2, so I can say the summation from I equals 1 to n of xi, wi has to be equal to total weight. We already say it was the summation from I equals 1 to n of wi times x bar. So if I solve for x bar is going to be equal to the summation from I equals 1 to n of xi wi divided by the summation from I equals 1 to n of wi, and this will determine the x coordinate of the center of gravity. Now if I want y, then you have to do kind of a rotation of axis, because I'm applying moment principle here, and then I can say that because the object is waiting, the weight of the object is acting in this direction, I can measure this distance. So what I do is something like that, and I say, oh, now the weight acts like that, and then I'm measuring this distance, but it's the same thing. So at the end I'm going to have that y bar is the summation from I equals 1 to n of yi wi divided by the summation from I equals 1 to n of wi. And you can do the same thing from z bar, or the z coordinate of the center of gravity, summation from I equals 1 to n of zi wi divided by the total weight, which is the same thing that this is the total weight. Perfect. That will allow us to calculate the center of gravity of any shape. Now, what happened if we are working with the same type of gravity? The gravity doesn't change, and we don't have those weird microgravity differences. And then what happens is, the weight is going to be equal to the mass multiplied by the gravity. And if I substitute that into this equation, then I'm going to have what? I'm going to have the summation for x bar, for example, is going to be the summation from I equals 1 to n of xi multiplied by wi, but the wi is going to be mi multiplied by g, which is common to every single one of the terms because it's not changing, divided by the summation from I equals 1 to n of mi multiplied by g. Now this g can go out of the summation because it's constant, and that means that this is going to cancel. And then I have the same expression of coordinates, but in this case we are not talking about the center of gravity. We are talking about the center of mass, because we're assuming gravity is constant. Now what happens if I use the same equation now? The same equation of the mass. And now I say, something, not only I have a constant gravity, however, all the object has the same density. It's a homogeneous object. So if it's a homogeneous object, the density of that object is mass divided by volume. So what if instead of mass I change that mass and I put mass is going to be equal to density, which is going to be constant for all the objects, multiplied by VI. Now, if I plug this into here, then the mass is going to be changed by this, and the mass is going to be changed by this. The raw value, or the density value, is going to come out of the density, out of the summation, in the same way that the gravity went, and that equation could be expressed at the center of volume. VI now divided by the summation of the VI's, or the total volume. Now look at the same equation. I'm not changing anything. I'm just restricting and simplifying the properties. Now let's say that that object that we did before, this object, this weird object, now let's say that it has the constant thickness. Everywhere this thickness is T, let's say. The volume of this object will be the area of the face multiplied by T, and the area of each one of the little pieces will be also AI multiplied by T, because T is constant, it's a thickness, constant thickness. So if I put that into this equation, now look what happened. The whole equation get transformed into x bar equals the summation of I equals 1 to n of xi, but in this case it's going to be multiplied by this, and this thickness is going to be on top and bottom, because this is AI T outside of the summation, and here summation of I equals 1 to n of, same thing here, AIT. Remember, this is the volume, but thickness is constant. I'm taking it out. This and this cancel out. And then I have the summation from I equals 1 to n of xi AI. And now we are talking about centroid of areas. And the centroid of areas is no other thing than the geometrical center of the shape, if you have, of course, the same density. Something like that. Anything lower that we can go to? Any dimension less? Well, you know, if you realize we're coming from, let's say, 3 dimensions with weight to 3 dimensions with mass to 3 dimensions with volume to 2-dimensional plane. What if I go to lines now? I can do that, because let's say that you are calculating the center, or you need to determine the center of, I'm going to draw something here that a lot of you know, something like that. And that's a hanger, a cloth hanger. Then this part is assumed to be constant also, and when you calculate this is just using the length instead of the area, because the cross-sectional area is negligible with respect to the length. So I'm going to have xi li divided by the summation from I equals 1 to n of li. And now if I make these little pieces really small, what is going to happen is that those little pieces becomes integrals, and then I can express my equations. I'm going to use the area, but it's the same equation that applies to everything. The integral of x dA divided by the integral of dA. That's for x, and for y should be the integral of y dA divided by the integral of dA. And that's basically the way, or one of the ways, that you can calculate the centroids of an object. Now let's start with a really easy shape, just for simplifying this project, and let's do something that you know. Let's determine the centroid. This is the way you're gonna see it. Basically, determine the centroid, or the center of mass, or the center of gravity. But in this case, I just want to calculate a very basic shape, which is this one, and this is B, and this is H. So determine the centroid of that shape. Okay. First, copy the equation. Like that. And same thing for y bar. And let's start with x. The first thing that you have to do, you're going to measure a value of x, and you have to divide this in a small differential of area. And if you look forward in the other videos, I'm going to show you different methods for doing this. You can use the same differential of area, or you can use even double integrals to do that. But this is explained in a different way, in the different videos. I'm just going to guide you through this very basic example here. What I like you to do while you're learning how to do this, the first thing that I want you to do is that please select your center, your axis of reference. And where are you going to select the axis of references? Well, the axis of reference, you're going to select them in any way, because in any position, because those are axes of references. Now, try to wherever you want to, and whatever position is the easiest position for you. My experience tells me that the easiest position is placing the center, the axis of references, of the axis of reference as close as possible to the figure, and keeping all the figure in the first quadrant. This is important. As close as possible to the figure, and placing the whole figure in the first quadrant, which makes basically this location for the center of gravity, for the axis of reference. Now, the second thing is this. If I'm calculating xy, I'm measuring x. So you are measuring an x distance from that axis of reference. Now, the first method that I'm going to explain you, which is the easiest one to digest, is this. If you measure the distance horizontally, I'm going to put my differential of area perpendicular to that. And this is going to be my differential of area in this case. Differential of area in that equation. Now, if this is x and this is the differential of area, this distance here is going to be dx. And I know this height is constant in this case. If it's not constant, I have to look for an equation or something like that. But in this case, it's constant. So my differential of area is going to be h multiplied by dx, base times height, h multiplied by dx. The only thing that I have to do now is put everything into that equation, and then I can get that x bar is going to be equal to the integral of x multiplied by dA is h dx, divided by the integral of dA, which is the integral of h dx. From where to where? Well, from where to where is this? You're going to take this differential of area, and you're going to sweep the whole figure with that differential of area. So that differential of area is going to start from this part, and you're going to sweep the whole figure until you reach the end of the figure. Meaning, you're going to start from 0, and you're going to end in B in this direction. From 0 to B, from 0 to B. To be or not to be? That is the question. So then I get this part here. This h is constant, as I said before. I can put it outside, and when I do the integral, it's going to be x dx. The integral of x dx is equal to x squared divided by 2. The h is outside, and this is from 0 to b. And in the bottom, this is the x goes outside, and this is just h times the integral of dx is x from 0 to b. So when I solve this, I'm going to have h multiplied by b squared divided by 2 minus 0 divided by h times b, evaluated, that part, minus 0. This and this cancel out, this and this cancel out, and you have b divided by 2, meaning that the x is going to be in b divided by 2, which is what we knew, because we knew from before that the centroid of that figure should be there, and if this is b, this is going to be b divided by 2. Now I can repeat the same thing, and I can do now the using this equation for the y coordinate. If I use that, I use the same principle that I was explaining you. Now I'm going to measure a y distance like that, and I'm going to select my differential of area perpendicular to my y distance. This is going to be my new differential of area. There's another approach that I can use the same differential of area for that, and I explain that in future videos, but for the time being, this is the first one. So this is going to be y multiplied by this distance here is going to be dy, and this now is constant and is b, so this is going to be equal to b times dy. If I use that, then I'm going to have that y bar is going to be equal to the integral of y dA divided by the integral of dA. And y dA is what? The integral of y multiplied by dA. By dA is this, b dy. From now, I'm going to sweep my shape from here to there. That's what I'm doing. So it's going to go from 0 to h. From 0 to h. What is the integral of dA? Yeah, I know the integral of dA is the integral of b dh. Yeah, but this is a rectangle, right? This is a rectangle. The integral of dA is a. And if you know the a, you can put here directly b times h, which is this. But you knew it, so don't waste time doing that unless your professor really asks you to demonstrate everything. I don't. So then when you do that, this is going to be by squared divided by 2 divided by bh from 0 to h. And when you put that into here, you have bh squared divided by 2 divided by bh. Cancel, 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 cancel. H divided by 2. H divided by 2, which is what we knew from before. Now, rectangle is easy, but I have seen so many people failing into this because they get a different value for this h divided by 2. Let's say they get h divided by 3, and they don't even question themselves. My next step is getting those distances, and then I do what I did before. I place my center of gravity based on those coordinates, b half, h half. And I do a quick analysis, visual analysis of, does that make sense or not? Well, yeah, I know that for the rectangle, the center of gravity should be there and it makes sense. But I just want to be sure that this is what is going to happen. And that's basically what I have for you. I mean, this is the centroid of that figure. Now, what if I select a different type of figure? I'm checking here if I have a triangle. I don't have a triangle, so it doesn't matter. Let's do a triangle. Let's do a triangle, and I don't need the equation of the triangle because it's really easy to do. This is improvising, okay? Improvising. Live television. So now, determine the centroid of the triangle. This triangle here. Okay, I'm gonna do the first part. X bar equals the integral of x dA divided by the integral of dA. And the integral of dA I know is a. I know this is a, and I know the area of that. So if I know the area, once again, I'm not gonna go through the whole process. I'm just gonna call it a. X dA divided by a. Okay? First step, what is the first step? Locate the axis of reference. Where I'm going to locate the axis of reference? Wherever I want. What is that wherever I want? As close as possible of the first figure, and placing the figure in the first quadrant. That's the location, my preferred location for that triangle. Okay, this is B, and this is H. Those are given, those values. And my intention is to locate the centroid of that shape. Now if I locate the centroid of that shape, let's start with X. I'm measuring X. That means that I'm going to measure this distance X, and my differential of area is going to be perpendicular to that X. That is my differential of area. I know this distance is going to be the X. How much is this distance? And people say 0, people say H, people say H divided by 2. And none of the answers are correct. This distance is determined by this line and this line. This line is just the equation of that line. What is the equation of that line? Well, I know that y equals mx plus b, where b is the y-intercept. In this case, the y-intercept is 0. So the equation y is going to be equal to mx. And what is the slope of this line? Rise over run. So y is equal to h divided by b multiplied by x. That is giving me the height at any point. Now if you want to be sure about that, just try it and say for x equals 0, you're here, right? Y equals 0, good. For x equal b, when you are at this end, you put b over there, b over b, cancel out h, good, that's it. So my differential of area is going to be h divided by bx multiplied, which is the height, multiplied by the x. Done. I just have to put this in here and solve that integral. So my x bar is going to be equal to x, the integral of x multiplied by dA is this, divided by the area. But the area of the triangle, well, you can put the integral of dA and do this integration if you want to, but I know it's BH divided by 2. That's the area of the triangle. Now, from where to where? Well, I'm sweeping this section with this differential of area. I don't care if my differential of area is growing, but it's going from this end to that end, from this end to that end, from 0 to b, from 0 to b. And now I solve this. So this is going to be h over b goes outside the integral, and then you have integral of x squared dx divided by bh divided by 2. And then if I do this, this is going to be h over b, this is going to be x to the third divided by 3, bh divided by 2, and this is from 0 to b. When I do the substitutions that I have to do here, this is going to be h over b multiplied by this, but this is b to the third divided by 3 minus 0, and this is going to be bh divided by 2. And now this h and this h cancel out, this b and this b to the third becomes to the second, and then this b and this b cancel out, and then this 2 passes to the top and this 3 goes to the bottom, and this is 2/3 of b. So my x coordinate is going to be 2/3 of b, which, if you remember, 2/3 from the acute angle, 1/3 from the right angle, so that is correct. Now what happens if I ask you to do the same thing, but now in this occasion you're going to have to do y? So that means you're going to be measuring y, and my differential of area is going to be in this direction. Usually I give my students some time to do this in the classroom, and I say, now I did this, now you do the other one. And then when they do the other one, they don't want to think, and they just go and reproduce the same steps that I did and say, oh, if in this case it was h over b, in the other case it's the same thing. Now look what happened here. I'm going to do this example because once again, I'm telling you, it's an easy example. Like everything in this class is easy, but it's so easy to mess up also in this class. So we're going to do now y bar. Y bar is the integral of y dA divided by the integral of dA. That's what y bar is. And I said, if I'm measuring y, I'm going to measure y in this direction, and my differential of area is going to be in this other direction. No questions. This value here is the y. How much is this value here? Well, you know, this is b, and this is h. And we already calculated the equation of this line, y equal h over b times x. That's the equation of this line. So how this differential of area is determined, or this length, is this line, which basically this line is x equal b, minus this line. So I'm looking for this coordinate minus this coordinate. That's what I'm looking for. This coordinate minus this coordinate. What is this coordinate? This coordinate is this coordinate, we already did this. We did that? No, we did the other one, right? XDA. Okay, good. XDA, we did XDA. Yeah, and we're doing y times this. Yeah, that's what I have to do. Okay, this minus this. So what is this? What is this point here? Because this h over bx is giving me the location of each one of them, this part here. But if you realize this location, if I say x is going to be what? B over h times y. This is x. Now the important part here is realizing that that x is not this. X is this. Because if I'm saying this is a point, any point, the coordinates of this point are x, y, basically x is this distance, or x is this distance, or x is this distance. But I'm looking for this one, not for this one only. So this is the distance that I'm looking for, and that distance will be b minus x. That's what I was telling you. It's the difference in coordinates between this line. This equation will be x equal b, and this equation here will be x equals b over h y. So basically the distance that I'm looking for is this value. I'm going to call it x2 minus x1. That distance, or my differential of area, is going to be this value, x2 minus x1, x2 minus x1, multiplied by my dy, because this is dy. What is x2? x2 is b. What is x1? x1 is b over hy dy. And that's basically what you came with. Now you plug this into here and you solve. How do you solve that? Y bar is equal to the integral of y multiplied by this, b minus b over h y multiplied by dy divided by the integral of the dA. I'm gonna say bh divided by 2 because I know that's the area. And once again, this goes from this point to that point because the sweeping goes in this way. So from 0 to h. And now you separate this into two integrals. So you have the integral from 0 to h of b y dy minus the integral from 0 to h of b over h multiplied by y times y is y squared dy. This is b over h dy. bh divided by 2. And now you solve for this. When we solve this integral, you have b y squared divided by 2 minus, and this is going to be y to the third divided by 3, b over h y to the third divided by 3 divided by bh divided by 2, and this is from 0 to h. And then from here it will be bh squared divided by 2 minus, this is going to be h to the third minus h here, cancel, so it's going to be bh to the square divided by 3 bh divided by 2, and this is basically 1/2 minus 1/3, so it's 1/6. So 1/6 of bh squared divided by bh divided by 2, cancel, pass to the top, bottom, y bar equals 1/3 of h, which is this part here, 1/3 of h. What is the next step? Locate your coordinates. 2/3 of b, that was x, we calculated before, somewhere here, and 1/3 of h, somewhere here, 1/3 of h. Centroid, right there. Does that make sense? Can you think keeping the equilibrium of that shape if you put it flat in that point? Yes, that makes sense. And even if you don't see it like that, you knew these values from before, because when we studied distributed loading, you knew these values from before. What is a better and easier way of doing this if you don't have to follow that longer approach? Just rotate your figure. If you have that figure there and I don't want to deal with those distances, rotate it, and now put the figure like that and invert your axis and calculate your figure like that, and it will be easier. Try rotating your axis, try rotating your figure, but remember, if you rotate your figure, you also have to express your coordinates based on the rotated axis that you are using, and then transform those into the original axis. But this is all for center of gravity and centroid that I have for this introductory lecture. I have a bunch of problems solved in this topic, so go and check it please, and I'll see you in the next videos. Have a good day.